Okay, but what is the spectral phase? What is it? We keep harping on a phi of omega. What is it? How do I measure it, say visualize it, understand it, and whatever not? Okay. So, now let us consider the following. Recall the resonator we had discussed earlier in this course, like the echelon. That is why the echelon is such a great example for okay, something like that maybe. Pardon my poor drawing for a moment at least. That is the echelon, right. So, what its transmission spectrum had this, it had specific modes centered at say omega naught, omega 1, omega indexed with -1, omega indexed with -2. It does not mean that they have to be negative, I am just pulling out some labels for it, and we had here an intensity, right, transmitted intensity. So, we had different frequencies, okay, or let me label it according to what is here, omega 1, 2, 3, 4 and so on. Now, if I now spread these frequencies out in time, I take omega 1, sketch my omega 1 as it should be, sorry. This is my omega 1, this is omega 2. Okay, these do not quite look like the resonant modes of a resonator, but I am just giving you an example, because it is not as if this is a multiple of this and so on and so forth, as if it is not as if this is 2 pi over t and this is twice 2 pi over t, this is thrice 2 pi over t and so on. But modes, yeah, some resonant modes, we can still consider these coming out of as waves coming out of resonators. So, we have 6 monochromatic waves here, and note that all of these in our current description lend themselves to being described as cosine some omega I of t in the field of the ith mode is an amplitude, some amplitude multiplying cosine omega t. There is no initial phase factor phi associated with any of them. Point clear? So, then that simply means that at t is equal to 0, maxima align themselves nicely across the 6 frequencies going from omega 1 to omega 6, correct. So, now let us sum these up as we do in the case of a Fabry-Pérot. Let us find out the sum of these fields at all values of time, all the way from some negative value of time to positive value of time. Okay, let us sum this. We do, join me in doing this visually. Maxima all add up at t is equal to 0, and then the amplitudes in each case starts to fall, okay, at some rate depending on what the value of the frequency is. Around this 0, okay, the maxima start to decline, and at some point one of these pulses has started to take negative values. You see, it is reached a negative maximum, whereas this pulse over here on top still has a, okay, this is also taken a negative value, right. So, let that be as it is. If it is fields, yeah, fields will take negative values, right. So, close to 0 they add up the best, they interfere most constructively, elsewhere they start interfering say destructively. For example, take the next maximum here, it coincides with the negative maximum for the last frequency omega 6 more or less. So, they start to cancel out each other, if we can visualize it somewhat like that, right. Therefore, the sum of these waves will end up concentrating, okay, non-zero maximum field amplitudes, irradiances and energies in this region, right. In the region around 0, the energy in the pulse gets concentrated essentially. Agreed? So, this is the region where the pulse amplitude is going to be non-zero, whereas everywhere else the constituent waves start to cancel each other out, and that is the pulse for you and me and everyone. So, this pulse is a coherent sum of all these constituent waves. Yeah. And here we did this thing of starting out with these pure sinusoids which are cosine. You could have started with sine. If you had started with sine of omega it plus 0, doesn't matter actually, you would have found a maximum somewhere else other than 0. You just found it pi over 2 phase away from the 0, right. So, that is all, but then as a consequence of this, we have lined up these pulses, the maximum of the pulse at time t is equal to 0, and that is what it means. So, therefore, these frequencies and their relative phases, here we set the frequency dependent phase factor to 0, and we had this as a consequence this. So, the spectral phase is the phase of each frequency in the waveform. Great statement, but where is the 0 of this scale? This scale of spectral phase needs to have a 0. I am going to claim that what you need is the relative phase difference between successive frequencies. You can pick the spectral phase of any one of these frequencies and say, ha, that is the 0 for the spectral phase meter, and the relative frequency phase difference between the spectral phase of a chosen reference frequency and that of others is all that matters when we add up these waves and sum them up, right. So, we have got to start somewhere and we could do that. Now, consider this graph where what have we done? We have shifted these cosinusoids in the following way. This is in the red case cosine. This is a function where we have cosine of omega 1 t. Sorry, let me take a bit of time to do this well. This is cosine of omega 1 t plus 0 times omega. Now, the next guy is cosine omega 2 t. No, sorry, there is no omega dependence over here. This is just plus or 0. Sorry about it. It's a value, right? The dependence will have to be pulled out by us, plus 0. Now, here what have we done? In the next case, look at this, the maximum is shifted by a wee bit, about 20% of pi. So, this is 0.2 times pi. Okay, here I should have written it more. This is what I intended to do, 0 pi, 0.2 pi plus a 0.4 pi plus 0.6 pi, 0.8 pi. All of these are essentially captured in by how much the maximum has shifted away from the 0 of the time axis. Right? Fair enough. So, we can capture much of this in writing it like this, that this is a sum over some index. What should I use for the index? Okay, we can use say q, where we essentially have that is the sum of cosine of omega q t plus 0.2 times or q multiplying 0.2 pi. Okay, if this is the amplitude of interest and I am summing over these q's going from 1 to 0 to 6, right, then the set of shifted sinusoids does the following. Now, let us look at what does it look like at t is equal to 0. There is a maximum of omega 0 and the sort of positive maximum of omega 1. Okay, I am making some mistake with my indexing. I will fix that. Just a moment please. Yeah, so I should have made this omega of q plus 1 to make it consistent with the way I have written the omegas and the q's over here, right. So, this should become phi. Okay. Yeah, now it's fixed, but let us come back to the point we are trying to make here. The positive maximum of omega 1 and the negative maximum of omega 2 are aligned for this time value, and we can walk through these others and find similar pairs of nearly cancelling amplitudes across different frequencies. Therefore, we can say in this exercise on visual math that all the amplitude here for the summed up wave is going to be 0. But I walk forward and then here comes a sweet spot. At this location, the frequencies are aligned, my stars are aligned, or I could have looked at this, look at this, the maxima all of them got shifted linearly. That is because we have added linear phases, okay, with the line with a slope of 0.2 pi to this entire mix of things, right, but they were constant for all time. That is the important part. This phase addition to wave of every frequency was constant throughout time. We just shifted the waves all to the right by different amounts in some sense, but now here they seem to have aligned up, right. So, therefore, at this point there is an alignment and there is the pulse. Okay. So, what essentially happened? What essentially happened is, as compared to the previous view graph, the same pulse, the grey curve, the pulse has moved in time. We took a snapshot at an instant, we found the pulse somewhere, we marked it time t is equal to 0 at its peak, took a snapshot later, the amplitude, we found that the pulse is elsewhere, the horse has moved forward. But what happened accompanying this propagation? What happened is this thing here. You see, the maxima closest to t is equal to 0, give us the picture and the impression that they have all been shifted away from 0 by some amount. So, if you want to really construct and so the pulse in a way is sort of getting reconstructed at every moment in time when it is propagating, and there is a nice symphony of its constituent frequencies. Okay, they know how much to move by in terms of their phase. Of course, they have no cognitive abilities, but if I were to think of it in as a sci-fi movie scene, it would be kind of like that, right? They would all be shifting, each of them tick, 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 tick down, and that's how the pulse moves essentially, right? So, that's the beauty of describing pulses in the spectral domain. So, a linear spectral phase shift connotes propagation. Okay. So, this is what occurs in terms of the shift theorem in action, or that is the propagation of a pulse, right. It's kind of beautiful, isn't it? So, now we will probably close with this for today. We have been talking about frequencies, right. We have been talking about frequencies, but what we measure more often than not in a laboratory spectrometer is wavelengths. Of course, you can challenge me by saying, hey, but what is the big deal, right? After all, we know for a fact that C is nu lambda. So, how C, especially in the vacuum speed of light, is a universal constant. For a medium, the speed of light is a constant in a given medium, but still they are both related to through a physical property of the wave. How does it matter whether I measure frequencies or wavelengths? Well, it is the following: you have the same spectral content, whichever variable you choose to measure in. It's just that you map every bit of the spectral content, either the lambdas or the nus. You are going to map them to another coordinate and then do the measurement. We simply do not have the ability to directly measure them for whatever it is worth. We map wavelengths onto some spatial detector, right, and we map frequencies. We could possibly map we map this to some kind of at times temporal detector, a detector which can measure, a device which can measure and record a value of something as a function of time. Okay. So, or there could be other means. All that we want to differentiate is what we are, how we are doing the measurement of the spectral content. If we do it in terms of spatial coordinate, and then we are talking about the spatial periodicity of the wave. We are mapping the spatial periodicity onto different points on a detector. That's a wave with a certain wavelength, say lambda, propagating towards you, goes through a dispersing device and reaches a detector plane, where the detector is say segmented, whereas another wave with a different wavelength goes to the detector plane. Okay, I could sketch this better. Device, and this pushes this wave onto some other location, whereas this is my detector. So, this is a typical wavelength measuring device, okay, a wavelength dispersive device. Which we call in common, more commonly, a spectrometer. So, then we are measuring wavelengths. This is easier done, as simple as that, because this dispersive device or dispersive element, dispersing element of this device is a prism or a grating. So, now the same spectral phase can be transformed from the frequency domain, which is what we have been doing so far, writing this out in terms of these omegas, where omega is 2 pi c by lambda. Okay. It had a functional form phi sub omega, while the same information transformed to the wavelength domain, it would be phi sub lambda. The index and the subscript keeps track of whether it is wavelength or frequency. So, these two are equivalent descriptions. The same spectral phase is kept track of. That is to say, okay, if omega 1 corresponded to lambda 1, then the spectral phase corresponding to that omega 1 or lambda 1 has the same value, omega 2 lambda 2. If omega 2 had a relative spectral phase of 0.2 pi relative to omega 1, then lambda 2 corresponding to omega 2 related as omega 2 is 2 pi c by lambda 2 will have the same spectral phase, that is 0.2 pi, and so on. So, this is just such a function, but frequency and wavelength are sort of not linearly related, right, because of this equation. That is to say, nu is c by lambda. Okay, therefore, the now the whole point of all this is the following, that we essentially bother ourselves with measuring out, or we would like to measure, or we have described the pulse in terms of s of omega. The spectrum of the pulse is s of omega, because we think of the pulse in terms of time, we did not think about it in terms of spatial variables. Okay. That is another story for another day maybe, but then it is time frequency description. So, s of omega is here, but what we more easily measure is lambda, okay, in the laboratory. So, what we will end up measuring is spectrum in terms of lambda. So, s sub lambda, the subscript, although tiny, is critical here. S sub lambda of lambda is what we are measuring. Okay, so, from this knowledge of this, we are going to get a knowledge of s of omega for the sake of our physics, mathematics, theory, and whatever not, right. So, if I want to measure a spectrum of a pulse and do some computation on my very real measurement, then I would essentially need to convert my wavelength spectrum into my frequency spectrum in order to take my business forward, right. So, transform the spectrum. How do I do this transformation? What is my bottom line? The bottom line is the so called energy in whichever domain I am. One of our favorite conservation principles is energy conservation. This is not even an instance of conservation. This is just you can say maintaining the integrity of our discussion, that if my description of the pulse comes out as the pulse having so much energy in the spectral domain, then my outcome of whatever processing I do to or fro the wavelength domain should have the same amount of energy. Just the math cannot create or destroy energy, right. That is all we are trying to make a statement of. So, since the spectrum of the pulse, let us once more think about this with as much care as possible. A thin slice centered at omega 1, okay, would have had so much energy, that is, it would be s omega 1 multiplied by some small delta omega, that is the energy contained here, then S at omega 2 multiplied by delta omega. So, we essentially need, of course, we need to keep track of the kind of variable that I am creating. So, this would have been like something like delta S1, this is delta S2, this is delta S3, it's delta Sn, or add all these deltas and you get what I would call the pulse energy. Now, whether you do this in the frequency domain or the wavelength domain, it should give you the same result. So, we are now going to make use of this salient feature and say that this is a common quantity before and after transforming from either wavelength or spectral domain, right. So, take note of this and then say, okay, I want to relate S lambda to S omega. That's all we are trying to figure out how to do this. Okay, in terms of math, it's very simple. There must be a Jacobian factor, just find it out and get on with life, right. Exactly what we are doing. So, change variables. All we are going to say is, okay, here you have on the right hand side S of S omega, right. So, take that, write down both omega and d omega in terms of lambda. Omega is 2 pi c by lambda, d omega is d lambda multiplied by 2 pi c by lambda square. That is, do some calculus on, take the derivative of omega with respect to lambda, do the calculus there and you get a factor, the prefactor that multiplies this, okay. And then you essentially have that this is now S of omega multiplying of, which is a function of 2 pi c by lambda, and you have this multiplicative factor 2 pi c by lambda square. Okay, this negative sign is a consequence of the math, but energy is a positive valued variable, right. So, keep track of that too. And now, we have the opportunity to relate by comparing the, forget all this stuff, compare the integrands of the two integrals over here. S lambda is therefore equal to this quantity. So, S lambda is S omega multiplied by 2 pi c divided by lambda square, 2 pi c divided by lambda square is the Jacobian for the transformation from omega to lambda. Of course, if one recalls or the courses on calculus, differential and integral calculus, is what we must have learned long ago or not so long ago, and just pick up the Jacobian and multiply it and you get the new form. So, but then what does this physically mean? We must think about that as well. It simply means that if you had a nice Gaussian in the frequency domain, what I mean by nice Gaussian is a very symmetric Gaussian about some central frequency. It's very symmetric about this, right, sort of a mirror image across this line. We now multiplied this function, okay, with 1 over lambda square in the transformation and skewed it across a line that drops from the peak of this function down to 0. So, the Gaussian has gotten skewed, that is it. But then remember, the other important factor is the spectral phase correspondingly, which was just a linear a line in this case for a pulse that is Gaussian and real, and it has nothing much else to it. In the wavelength domain, it actually becomes kind of has a quadratic behavior. This actually is something that we must always remember in time, because we will later on consider the time bandwidth product of pulses and consider the notion of a transform limited pulse, and the so called chirp pulse and so on and so forth. There the shape of the spectral phase function will matter, and we should there be extremely careful, and I will remind you about it as to how the spectral phase behaves, but then pay attention to what is the variable which we are using to describe either frequency or wavelength, right. So, that is a Gaussian spectrum, which is in linear spectral phase versus frequency as well as wavelength. Okay. Now, we have well past our time at the moment. So, I would leave this as an exercise for you to try out. Consider a pulse with a width of 1 picosecond, compute its bandwidth in the frequency domain using the relation delta nu delta t is about a half, okay, sort of the uncertainty principle, and then transform the width into wave number units, which is 1 over lambda, but measured in centimeter inverse, and in wavelength units, considering a central wavelength of 800 nanometers, and convert the half a gigahertz bandwidth of the pulse to a wavelength, a bandwidth in wavelength, which should turn out in this case to be a nanometer. But please do this and convince yourselves. We will revisit this in the next lecture or perhaps the next tutorial. Okay. So, that's that for today in terms of our lecture and class. Let us keep in touch through this. So, we will stop here the lecture part, and we can discuss anything that the students either in person, there are only students in person, none online are. So, with that I will close today's lecture. Any questions, comments? So, then thanks for coming today, because today was kind of not the regular class, but in a way it's very encouraging for me that you came for the extra lecture. Thank you so much.